Okay, so welcome back. So can you hear me?
Yes.
All right, so let me just like stop again, and then because I feel like from the lack of reaction that the effective action has not really been communicated that well. So so what is an effective action, right? So it basically, you have, say, for all the points on some manifold, if there exists a G such that G acting on X equals to X means that G is E, that this is the only possibility, then the action is effective. Okay? So if there's some element that for which is not the identity element, for which which leaves all the elements invariant, then that's not an effective action, right? Okay. So what would be an example of an action that is not effective? Can someone come up with an example? I actually haven't thought about it, so I don't have an example ready, but we should be able to, right? I mean, to understand something, you have to understand something that is, you have to understand the counterexample, right? So can we come up with some group action such that it's the manifold it's acting on which is not, yeah. And I think Saif was trying to figure that out by when you said that would 0 degrees, 360 degrees be identified with 0 degrees, right? Saif, that was what you were trying to do, right?
Yeah.
Yeah, yeah, I see. Okay, so let's think about it and come back to it later. So, I don't have a good example handy, so, so that means that I haven't really understood the concept myself. Okay, so, but we'll circle back to it next time, okay? Or if someone has some, comes up with an example, let me know, okay?
I have a suggestion, but I don't know if this works. What happens if you rotate, for example, a hexagon by 60 degrees? It looks identical, but I suppose the points still go to different points, so it's not effective.
Yeah, exactly. It is not effective then. Yeah. No, it is effective. That's the point. It is effective, right? We want something that is not effective.
Oh, right. Yes. Yes. Exactly.
Yeah. Okay. So we'll come back to this. So, but one of the things that the group actions kind of lead us to another, a very natural idea. So suppose that this is the manifold on which, the group acts. And so you start with some point and you apply the group. And then what happens is that you end up in some other point X prime, right? So these are basically, they look like orbits, right? So they look like, these are called orbits under the group action. Okay. So another way of thinking about it, say, suppose we have a position vector in R3. So a position vector in R3, right? Now, if I apply all the elements of the group SO3, and we basically go to all these other points and they form the whole two-sphere, right? So, or suppose that, we look at, say, the point on, say this point. So this is my origin, and this is the vector, and this is, say, the z-axis. And I apply rotation around the z-axis, right? Then what I find is that the vector will then, it'll just trace out a circle, right? So this is an example of an orbit of a group action. So let me just define what the orbit is. So this is just that was just introductory heuristic remark. So the definition of orbits is the following. The orbit, say, the orbit of a point P in M is a subset, defined by, so we write it as GP, where G is the group. It is the subset defined by the action of the group on that point for all G's in the group. Okay? So now the comment is that if the group action is transitive, then the orbit is the whole manifold itself, right? So example of an orbit is that so SO3, if I take SO3 to be some group, and the manifold is S2, then the orbit of any point on S2 is S2 itself, right? Is this clear what I'm saying now? So what I'm saying is that if you start with some point on the two-sphere and you apply SO3 elements on the two-sphere, you basically generate all of the two-sphere. So the two-sphere is the orbit of any point on the two-sphere, right? So, I mean, let's just take an example. Let's just, look at this more explicitly. So suppose I take the North Pole. So this is the North Pole on the two-sphere. And I start applying SO3, rotations. Suppose I apply rotations which are rotations around the z-axis, the North Pole doesn't move, right? Because it's a fixed point. But if I apply any other rotation, then it starts moving, and it starts moving. So, and I can, but if I apply it an infinite number of times, so suppose first I do a rotation, so I go around this, and then I do a rotation like this, right? And if I do a rotation like this, if I do all these rotation, in principle, there's an infinite number of rotation I have to do, but that's beside the point. I generate the whole two sphere, right? So the orbit of the North Pole, under the group SO3 is the two sphere itself, right? And that's because this is a group action that is transitive.
So it's the part of the two sphere that you can reach from the North Pole under the group action.
Exactly, exactly. And since it's a transitive, if it was not transitive, then of course, so for example, suppose I take SO2, right, SO2Z, which I'm calling SO2Z. And then of course, it's not a transitive action, right? And it's, and then the group orbits are circles. They are not the two sphere itself. Then the orbits are circles, right? Okay. All right, so it's a very, very it's a very general concept, but it's a very useful concept, So for example, groups themselves can act on themselves. So if I have a Lie group and G is an element of this Lie group, if I take, say, another family of elements, say G prime of theta, where I said this is a, suppose that this is a one parameter, the one parameter abelian subgroup, right? Do you remember those? They are defined by, you take one of the generators and you just multiply it by one parameter and you just range the whole parameter, and that gives you an abelian subgroup. Now, if I apply G prime on G, and then basically, as I change theta, what I do is that I move around the manifold, right? The group manifold. So if this was, say, if this was G, as I apply G theta, I move around the group manifold, and this curve is an orbit of that subgroup, right? It's an orbit of that subgroup. Okay, and if it's suppose it's a closed group, it might actually come back to the same place. In this case, it's kind of, it corresponds somewhat to our intuitive notion of what an astronomical orbit is.